Hi folks, and welcome back to our study of Taylor series, and that's actually the title of this section. And let me remind you of what we showed last time. We showed by using an IVP that e to the x is 1 plus x squared over 2 factorial, and so on. We showed that because we were able to show that, if we call that y, that dy dx is equal to y, and that y of 0 is equal to 1. And so we solved that IVP, and we were able to show that y is equal to e to the x. So at that point, the question presented itself, okay, how do I work directly? In other words, if I start off with e to the x, how do I get a power series, or a Taylor series, or a Maclaurin series? And that will be the work of this section, to show how we start with a function and get the Taylor series for it. So here's how we begin. We first begin with an assumption that f of x is infinitely differentiable over some interval I which contains a, and a is going to be the center of this Taylor series. So we begin by assuming that here is the Taylor series for f of x, centered at a. And really, our work is finding these coefficients. Once we know the coefficients in the general form for the a sub nth coefficient, we can write down the Taylor series. So the way this procedure works is we go ahead and we start taking derivatives. So the first derivative is just going to be a sub 1 plus 2 times a sub 2 times x minus a plus plus n times a sub n times x minus a to the n minus 1, and so on. So we're a little restricted here with the room, but what I'll do is take a few seconds and I'll write out the next couple of derivatives, and you'll be able to see where they come from. Okay, so here's f of x. When we take the first derivative, here's what we get. When we take the second derivative, here's what we get, and the third derivative, and so on. And so what you begin to notice is that the leading term of this kth derivative is going to be of this form: k factorial times a sub k. Here's the third derivative: 3 factorial times a sub 3. Here's the second derivative: 2 factorial times a sub 2. So the general form for the kth derivative at x is k factorial a sub k, and then a bunch of terms that all have an x minus a in it. So keep that in mind. So the second step in this process is to evaluate all these derivatives, including the original function, for x equals a. And what that will do is cause all those terms that have an x minus a term in them to be 0. So essentially the first term, f of a, is just going to be a sub naught. The derivative, first derivative evaluated at a, will be a sub 1. The second derivative evaluated at a will be 2 factorial times a sub 2. The third derivative evaluated at a is 3 factorial a sub 3, and the general kth derivative evaluated at a is k factorial times a sub k, and this pattern continues. Now, if you remember from what we said at the beginning, the whole point is learning what those coefficients are. So we'll kind of work backwards here. A sub naught is f of a. A sub 1 is f prime of a. A sub 2 is the second derivative evaluated at a over 2 factorial. And that pattern continues, and here's the big deal. The kth derivative, let's start again. I'll just get rid of that. So the a sub k is equal to the kth derivative evaluated at a over k factorial. And that is the big deal, and that really is the heart of this. And that tells us how to get the coefficients on the Taylor series. Just one thing to note in passing. This is our general formula for the kth coefficient. And in order for this to generalize to f of a, in other words, when k is 0, mathematicians make the definition, that 0 factorial is, by definition, 1. And that makes everything work out. Don't you love it when mathematicians make those clever definitions? So let's finish up our work here. What we have is f of x written as a Taylor series. And we can write that in sigma notation, which makes things a lot easier. So now putting these two ideas together, here is how we find the Taylor series for f of x. It's going to be the infinite sum as we go from 0 to infinity, but now let's remember what a sub k is. The kth derivative evaluated at a over k factorial times x minus a to the k. And there, my friends, is the heart of our work for how we find a Taylor series. Now, just to remember, if a is 0 and we're centering the Taylor series around x equals 0, we have a special name for that series and we call it a Maclaurin series. So let's just make a note of that. When a equals 0, we have a Maclaurin series. And most of the series that we will look at will be Maclaurin series. All right, so let's look at some examples now. Before we get into examples, I need to tell you one more definition. And what we want to look at now, I made another mistake. So let's make this be an n. So if we look at a finite sum, this is a polynomial. And we call this the Taylor polynomial of degree n. So n tells you the degree, not the number of terms, but the degree. And this is something that we will keep coming back to when we are looking more at how we approximate functions with a Taylor series. Obviously, we have to use a Taylor polynomial because we can't use an infinite number of terms. Okay, so we'll come back to that in a sec. Okay, so just to tie up this this work with e to the x, let's find its Maclaurin series. So if we start with e to the x, the first derivative is e to the x, and all the derivatives are e to the x. What could be easier than that? So if we evaluate these at 0, we get 1, and all of the derivatives evaluated at 0 are 1. So therefore our formula tells us simply that a sub k is equal to 1 over k factorial. So therefore e to the x is equal to 1 plus x over 1 factorial plus x squared over 2 factorial. We always want to write the general term, x to the k over k factorial, and so on. So it's that easy, believe it or not, to get the Maclaurin series for e to the x. Got it? So here's a more interesting and a little bit more challenging one. We want to work now for f of x equals ln of x, and we're going to center this at x equals 1 for obvious reasons. So here's f of x. Here's the first derivative, 1 over x, and the second derivative is minus 1 over x squared, and the kth derivative is going to be, well, it's going to be a plus or a minus, and it's going to be 1 over x to the k. On the top we're going to have k minus 1 factorial, and this is going to be minus 1 to the k plus 1. So take a few minutes and maybe fill in with a few more derivatives here until you actually see why this pattern works. So now we go ahead and we find the values for a's. So f of 1 is 0. Now you see why we have to evaluate it at some number other than 0. F prime of 1 is 1. F double prime of 1 is minus 1. And then the big jump, the kth derivative evaluated at 1 will be minus 1 to the k plus 1 times k minus 1 factorial. All right? So now we find the a's, and I know we're running out of room here. So a sub 0 is 0. A sub 1 is 1 over 1 factorial. A sub 2, that was a minus, is minus 1 over 2 factorial. And finally, I guess I'll just write it under here. A sub k is equal to minus 1 to the k plus 1 times k minus 1 factorial over k factorial. And let me just change colors here. This is simply 1 over k. So if we can write it down at the bottom, ln of x is equal to, now we're centering it at x equals 1, remember that, and so we've got to use terms involving x minus 1. So our first term is x minus 1, and then it's minus 1/2 x minus 1 squared. The next term would be 1/3 x minus 1 cubed. And the general term is minus 1 to the k plus 1 times x minus 1 to the k over k plus and so on and so on and so on. So I think I got that right. And that's the Taylor series for ln of x centered at x equals 1. You should be able to make sure that you can duplicate that work. Okay, so let's do one more, and let's look at the Maclaurin series for sine of x. So I'll write down a bunch of these derivatives, save some time. So as we take the derivatives, what you notice is the derivative of sine is cosine, derivative of cosine is minus sine, the derivative of minus sine is minus cosine, the derivative of minus cosine, and we're back to sine. So the derivatives are cyclical in a group of 4, and so they just keep repeating like that. So what we do now is evaluate these at 0. So f of 0 is 0. F prime of 0 is 1. The second derivative at 0 is 0, and you should be able to see now that all of the derivatives of even degree will be 0. The third derivative at 0 will be minus 1. The fourth derivative at 0 will be 0. And so if we start writing down what our a's are, a sub 0 is 0. A sub 1 is 1 over 1 factorial. A sub 2 is 0. a sub 3 is minus 1 over 3 factorial. A sub 4 is 0. And maybe the easiest thing now is to just write down what we have so far and notice the pattern. So given what we have, our first term is simply going to be x. Then we're going to have minus 1 over 3 factorial times x cubed. And you should be able to guess that the next one is going to be 1 over 5 factorial x to the 5th. And that pattern continues. And so what is our general term? Well, it's going to be some multiple of minus 1, and it's going to be an odd power, so it'll be 2n plus 1 over, whoop, did I leave out the factorials here? Over 2n plus 1 factorial, and you got to play around with it a little bit to see that that should be an n. And there you go. And that is the Maclaurin series for sine of x. So now that you've seen some practice on this and see that it's a fairly routine mechanical procedure, it would be a good idea for you to pause the video and see if you can write down the correct Maclaurin series for cosine of x, which is going to be a lot like that for sine of x, and the Maclaurin series for arctan of x. So here are two upcoming questions that we have to answer. The first one is, if we have any Taylor series, for what values of x will it converge? And what you should believe is that it will always converge exactly at the center. The question is, how far can we go on either side of the center and still get an infinite series which converges? And here's an important note. Once you fix a value of x, in other words, stick a value of x into a Taylor series, what we get is an infinite series. And an infinite series is either going to converge or diverge. And we will learn techniques to understand when an infinite series converges or diverges. And the second big question we have to ask is, how many terms of a Taylor series must we use in order to ensure accuracy to a stated, that should be stated degree. And the idea there, remember, is that when we use so many terms of a Taylor series, what we have is a Taylor polynomial. And the question is, how many of these terms must we use in order to be sure that we are within 0.0001 of what the actual value of that function is? And so both of these questions will be answered in the next section or two, and they're really at the theoretical heart of what we do with Taylor series. All right, so I think that brings us to the end of today's lecture. See you next time. Ciao, ciao.